Who gets what? Fair division of indivisible goods. Division of goods and chores is a daily life problem. Who does the dishes? Who cuts the lawn? Who cleans the floor? Or on the positive side, there's a bequest to be split among children. Or I bring sweets for my grandchildren and they have to decide who gets what. Today, we will discuss this problem from an algorithmic and a mathematical side. This picture shows you an ad of a Saarbrücken law firm. The text says, your brother enjoys your bequest in the sun. He really seems to enjoy life, right? He has a cigarette. He wears a fur coat. I don't understand why he wears a fur coat when he is in the sun. But anyway, he enjoys the bequest. Fair division problems are ubiquitous: dividing goods, divorce settlement, bequest, dividing chores, work, or household duties. There are two websites, Split It and Fair Outcome, that offer fair division algorithms. Not only humans feel strongly about fairness, animals do too, and I strongly recommend that you look at a video by Frans de Waal. He has carried out the following experiment. So this is an experiment with apes. These apes eat cucumbers and they love grapes. So they prefer grapes much over cucumbers. But they perform the following experiment. So the ape gets a cucumber, and in return he has to give the person who conducts the experiment, he has to give a little pebble. And this works perfectly 25 times in a row. Now in this experiment there are two cages and there are two apes next to each other, and they both train to return a pebble for a cucumber or a grape. So the first ape gets a cucumber and he returns a pebble. Then the experimenter gives a grape to the second ape and the second ape returns a pebble. Now the first ape sort of expects that he will also get a grape, but he gets again a cucumber, and he looks at the cucumber and he does not return a pebble, but he throws the cucumber at the experimenter. The experimenter gives a grape to the second ape, and then again a cucumber to the first ape. And now the ape goes berserk. He tries to destroy his cage. He again throws the cucumber at the person carrying out the experiment. So this experiment shows that also animals feel very, very strongly about fairness. Now this splitting problem is an ancient problem. It's already mentioned in the Bible. And in the Bible there is a protocol mentioned called cut and choose, which we have all used at some point in our time, in our lives. So let me read the Bible to you. When Abraham and Lot came to the land of Canaan, Abraham suggests that they divide it among them. Then Abraham divides the land to a left and a right part, and lets Lot choose. Lot chooses the eastern part, and Abraham is left with the western part. This is cut and choose for a divisible good. Land is a divisible good. Cake is a divisible good. But we today are interested in indivisible goods. So what does this mean for indivisible goods? So indivisible goods are goods like a car, a house, a toothbrush, which you cannot split in parts. So agent 1 partitions the set of goods into two bundles, and agent 2 chooses the bundle they like more. I use they as a singular pronoun. This is correct English, so I will not use he or she, but I use the neutral pronoun they. Now agent 1 is happy because they split in their best interest. That is, they maximize the value of the smaller bundle. Agent 2 is happy because they are allowed to choose, and they will of course choose the bundle which they prefer, so they get at least 1/2 of the total value. We have to be careful here. When I use the word value, value is always value according to their own valuation. agents 1 and 2 in general have different valuations. So what is the better half for agent 1 may be the worse half for agent 2 and vice versa. Or they may both prefer the same part. Now agent 1 might also be unhappy because they had to do the splitting. They're only guaranteed their maxi-min share, which is something which I'm going to define later in the talk. Agent 2 is guaranteed at least 1/2. So one can slightly improve upon the protocol in one then goes to a randomized protocol, namely both agents split, and then a coin toss decides who plays the role of agent 1. Then in expectation, both are guaranteed at least 1/2, but it's decided randomly, and both in the worst case, so after the coin toss, they are guaranteed the MMS value. I will come back to this best of both worlds scenario at the end of the talk. So let me introduce the problem formally. So we have a set n of n agents, and I will always use I, j for agents. Then we have a set of m indivisible goods, such as a house, a car, a toothbrush, and I will use little g and also sometimes little e for goods. Then each agent has a valuation, which is just a mapping from sets of goods to real numbers. And vi of s is the value of bundle s to agent I. And we only require that the value of the empty set is 0, and getting more never hurts. So if A is a subset of B, the value of B is at least the value of A. And evaluation is additive if the value of a bundle is just the sum of the values of the goods in the bundle. And in my talk, valuations are additive if not said otherwise. And the goal is to find a fair partition, so a partition of X of the set of goods into n sets, one for each agent, and Xi is the bundle assigned to agent I, and we want the partition to be fair, and I will discuss different notions of fairness. And fair division of chores is equally interesting, maybe even more interesting, but in this talk I will discuss on fair division of goods, so of desirable things. There are three main approaches to fairness: share-based notions. I want to get what I'm entitled to, so this means I look at the set of goods and I do a thought experiment. Then I say I should get at least this, and if I get this, I'm happy. Otherwise, I'm unhappy. For example, I might say I want to get 1/n of the total value. This is called proportionality. Then there is an envy-based notion where I do not care what I get, but nobody should get more than me. I'm happy if nobody gets more than me. And then there is something called actually the oldest notion, Nash social welfare. This assigns a fairness score to each allocation and maximizes the score. Fair division and more generally social choice, electronic commerce is a striving area of research. So before I come to fair division of indivisible goods, let me talk briefly about fair division of divisible goods. And this usually is called cake cutting. So the divisible good is a cake. And one goal might be proportionality. So every agent should get at least 1/n of the total value. So each agent has a value for the cake, and he wants to get at least 1/n of it. And this is not too hard to achieve. It was solved by Steinhaus, Banach, and Knaster in 1948. And the strategy is called last the manager. So imagine that you order the agents 1, 2, 3, 4, and so on. Agent 1 cuts a piece off the cake, which in his opinion, should be 1/8. And then he asks agent 2 whether agent 2 wants to cut further, or agent 2 says, no, pass, you can keep it, and so on. We go through. If one agent takes over, then he will get the piece at the end, and so on. So what should agent 1 do? Agent 1, the piece he cuts off, he might actually get. So he should not cut off less than 1/8, because if he gets it, he's pissed off. He should also not cut off more than 1/8, because if he cuts off more than 1/8 and somebody else takes it, the leftover piece is missing more than 1/8, and so is not guaranteed at the end his proportional share. A stronger notion than proportionality is envy, namely an NVP partition, which does mean what? I prefer, so xj is the piece that goes to the j's agent, xi is the piece that goes to me, and I should value my piece more than any other piece. This can also be achieved. It's much harder to achieve, and there is still an open problem, namely how many steps are required. It is known that you need to do at least n square cuts, so you need to cut into at least n square pieces, but the upper bound is a tower of n. Yeah? So there is a big gap between the lower and the upper bound on the number of cuts. Now we come to divisible goods. So I mentioned there are the three notions to fairness: share-based, envy-based, Nash social welfare. All three notions have their shortcoming. Share, this is a nice notion, but it is not guaranteed to exist. Yeah, I want to get what I'm entitled to. Envy, there is no guarantee for the value that I get, and it's not known to exist. So share, it's known that it does not always exist. Envy, it's open, and there is no guarantee. There is no guarantee for the value that I get. Imagine you have 3 agents and 6 goods, 3 pairs of shoes, always a left and a right shoe, shoes A's, B's, pair A, B, and C. And imagine the bundles are A left, B left, A right, C left, B right, C right. So nobody gets a pair of shoes. So let's say if I get 2 left and 2 right, that's worthless. So, or I get the left and the right, but not of a pair. So they will not envy each other, but they will also not get any value. And Nash, it assigns a fairness score to each allocation and maximizes the score. It's not clear what does it mean to me that an allocation maximizes the fairness score. Yeah, it's an overall, a global notion. Let's now start to discuss the 3 notions. Before I do this, let me mention that I worked mainly on envy and a little bit on the 2 other notions. And I worked together with a large number of people: Hannah Akrami, Noga Alon, Bhaskar Chaduri, Jugal Garg, Martin Höfer, Tilika Pelika Vita, Ruta Mehta, Pranavendu Mistra, Marco Schmalhöfer, Alkmini Skorica, Kolnus Shakarami, Giovanna Varitchio, Quentin Vermond, and Ernest van Weiland. So, share-based notions. Agents consider an allocation fair if they get their fair share. Well, you could say proportional share. Yeah, I want to get 1/8 of the total value. This is too much to ask for. Imagine you have 2 agents and 1 good. You have to, because the good is indivisible, you have to give it to one of the agents, and the other one, of course, will not get its proportional share. His bundle has value 0, which is not half of the total value. So we have to settle for less, and Budish introduced a very interesting notion, the so-called maxi-min share. So the idea is that I performs the following thought experiment. I partitions in any way he wants and gets the least valuable bundle. So the MMS value of agent I is the maximum over all partitions, and then the minimum value of any bundle in that partition. Again, the minimum value for I. And agent I argues there is a partition in which every bundle has value at least MMS, my MMS value. So I'm entitled to a bundle of at least this value. And if we all have the same valuation, I cannot do better. So in this way, he sort of convinces himself that he should be happy with the MMS value. And we say an allocation, a partition, is an MMS partition if it guarantees the MMS value for all agents. So for all agents, the value of the ICE bundle is at least the MMS value of agent I. Does this exist? Well, here is what is known. First of all, the computation of the MMS value is NP-complete. This is already clear if you have two agents, because it generalizes the partition problem. You have to know, whether you have the set of goods, can you partition it into equal parts or not? That's the partition problem. And then the MMS value will be 1/2 the total value or less. And the partition problem is NP-complete, so the computation of the MMS value is NP-complete. Cut and choose for two agents and additive valuations. It guarantees the MMS value to agent 1, and it guarantees proportionality to agent 2. Why does it guarantee the MMS value to agent 1? Because agent 1 chooses the partition, so he will choose the MMS partition. And it guarantees proportionality to agent 2 because agent 2 is going to choose. The MMS partition exists if M, the number of goods, is at most 5 more than the number of agents. But, this is an important negative result, an MMS partition does not always exist. This was first shown by Procaccia and Wang, and then by Feige, Sapir, and Tauber with, I would say, a cleaner proof and also with a stronger result. This is a paper I strongly recommend to read. So if MMS partition does not always exist, one looks for approximations. So can I guarantee a fraction of the MMS value for all I? And Feige, Sapir, and Tauber has shown that for 3 agents and 9 goods, you can always guarantee 39/40 of the MMS value, and this is best possible. It's a beautiful proof. So what they do is they first prove properties of an MMS partition for 3 agents and 9 goods. For example, that you can always arrange the goods in a 3x3 table, and for one agent the MMS partition are the rows, for the other one they are the columns, and for the third one they are sort of the diagonals. The MMS partition always looks like this, and then once they have characterized properties of the MMS partition, they write down an integer linear program which captures the conditions that they approved and solve this integer linear program with the computer, and they get the 39/40. In general, we cannot have that the alpha is larger than 1 minus 1/n to the 4. So in particular, alpha equal to 1 cannot be achieved, and the distance is at least n/4. And on the other hand, on the positive side, slightly more than 3 over 4 can always be achieved. 3 over 4 plus 3 over 4,000. And this is a paper by Akrami and Garg. And the open problem is the obvious one. Close the gap. I want to show you a little bit a half approximation algorithm, which is due to Jugal Garg and his student Taki. So first we can normalize the valuations so that the value of the entire good set is n for all agents. Then the MMS value is at most 1. And the algorithm is very simple. As long as there is an item G which has value at least 1/2 for some agent, give it to this agent and renormalize. Once all goods have value less than 1/2 to all agents, you fill bags, so you have an initially empty bag and you add goods until one agent says this has value, the bag has value more than 1/2 to me, and then you give the bag to I. And it's clear that every agent gets 1/2. It's clear in step 2. It's also clear in step 3. What we have to prove is that we don't run out of goods. It could happen that we run out of goods, and I briefly argue that we cannot run out of goods. So let's first see that step 2 does not hurt any of the other agents. So imagine we give a good to agent I, because it has value more than 1/2 to agent I, and look at the MMS partition of an agent K. Then this good G is contained in some bundle. And what we do is we delete this bundle and distribute the other items in this bundle over the other bundles. And then the minimum value of any bundle for K will not go down. So the MMS value of the agents go down go up in step 2. Do not go down. Now, step 3 reduces the total value of the remaining goods by at most 1 for any remaining agent, because all the remaining goods have value 1/2 for everyone. And when we fill the bag, we will give the bag away as soon as one agent has value more than 1/2. Since individual goods have value less than 1/2, the value of the bag will not be more than 1 to anyone. And that means in step 3, we reduce the total value by at most 1 in every iteration, and therefore we will not run out of goods. So this is a 1/2 approximation and a significant refinement of this approach gives the 3 over 4 plus 3 over 4,000. And the gap is, remember, the upper bound is 1 minus 1 over n to the 4, so there's a gap to close. This is all I wanted to say about share-based notion. Let me come to Nash social welfare. Nash social welfare is defined as follows. So you have your partition into bundles, and you do look at the geometric mean of the values. So you take vi of xi, you form the product, and then the nth root. So this is a geometric mean. This Nash value ranks allocations, and the Nash allocation is the one which maximizes Nash social welfare. And it satisfies some natural axioms. For example, more equal is better. If you have an allocation and the values of the bundles are closer together than another one, this is better. Giving one agent more without hurting the others is better. So that means the Nash allocation is Pareto optimal. The third property is very important. The optimal allocation is invariant under scaling valuations. So imagine I judge the value of a bundle in euro cents, and then tomorrow I judge it, I value it in euros. So the numbers are divided by 100. But that doesn't mean that the Nash allocation changes, because the Nash social welfare, there's just this factor 100. And Nash proved that this geometric mean of the valuations is the only measure satisfying these three properties. In Nash social welfare allocations are also NV-free up to one item, and this what it means NV-free up to one item, I will discuss in the section on NV-freeness. Now, can we compute the Nash allocation? Well, finding the Nash allocation is NP-complete in general. Again, this is even for two agents and identical evaluations, because again, if you want to split in two, you have to ask whether you can split in equal parts. This is the subset sum problem, and it's even hard to approximate. What can be done efficiently? There is a 1.45 approximation algorithm by Barman, Krishnamurti, and Weish. And I want to briefly discuss a dichotomy for two-valued additive instances. So imagine the value of every good for every agent is either 1 or S, where S is a rational number larger than 1. Yeah, so Vi of G is either 1 or S for every I in G, and this S is a rational number larger than 1. And then we have shown if S is integral or half integral, so S is 3 over 2 or 2 or 5 over 2 or 3, then this can be done efficiently. And otherwise, if S has denominator 3, so S is 4 over third or 5 over 3 and so on, it's NP complete. So let me briefly show you an algorithm for the integer case. So where the value of every good for every agent is either 1 or S, where S is an integer larger than 1. Let me call a good light if it has value 1 for all agents, and heavy if it has value S for some agent. And then the algorithm consists of two phases. The first phase is you assume that all heavy must be allocated as heavy. So that means if a good G has value S for some agent, you have to give it to an agent that values it at S. And then one can do the following. One determines a lex max allocation of the heavy items. What is a lex max allocation? You ask yourself, can I give one heavy item to every agent? Can I give two heavy items to every agent? Can I give three heavy items to every agent? You go up like this until you cannot. Let's say you can give 5 to everyone, but not 6. Then you have determined also, hopefully, the set to which you can give only 5. And then you continue with the others. And then at the end, you add the light items greedily. Greedily means you always give it to the agent that has a least valuable bundle. And this lex max allocation can be determined by a method that we all know, alternating path. So we allocate the heavy items arbitrarily, and as long as one can make bundles more equal, do so. Let's say we are in this situation, we have 3 agents, and agent A owns 1 heavy good, agent B owns 2 heavy goods, agent C owns 3 heavy goods. But agent A also considers one of the goods heavy that B has, and B considers one of the goods heavy that C has. And then we can improve because we can move this thing over here, and we move this thing over here. And then everybody has 2 heavy items, and this is better. Yeah? So we search for alternating path, because here alternating path means A likes this good and it's owned by B, and B likes a good owned by C. And the effect of augmenting an alternating path is that the endpoints A and C change the heavy parity, and the other nodes keep their heavy degree and thence their heavy parity. And you will not understand this sentence at this point of time, but maybe on the next slide. So not on the next slide. So in what happens if we drop this assumption that all heavy must be allocated as heavy? Then we simply do the following. We consider a best of agent, so an agent that has a maximum bundle, and we take a heavy item away from them and give it to a least of agent. It will be light for the receiving agent. We do this repeatedly, and the optimal allocation is among the constructed ones. This is not too hard to prove. Now, what happens for the half integer case? Let me again look at a picture. So here we again have three agents. Agent A owns a bundle of value 3 over 2, a bundle of and two goods of value 1, so he has 3.5. Agent 2 owns 3 light goods, and agent C owns a good of 3 over half and 1, so he has 5 over 2. Agent B has 3, agent 1 has 7 over 2. And the question is really, can we improve? So make all give 3. And let's assume the agent B likes the heavy good owned by A and the heavy good owned by C. Then what we could do is we could give the 2 heavy goods to B and move its 3 light goods to A and B, and then all 3 have value 3. Yeah. Now, this here is not an alternating path, it's a more general notion, because here we have this agent B, which likes 2 heavy goods, and both of them are moved to him. This, in alternating path, it alternates between owning a good and liking a good. Here, B owns 2. So, we all know how to search for alternating path. How does one find alternating walks? Now, if you look at it carefully, an alternating walk with endpoints A and C is really the question, is there an allocation of the heavy goods such that A and C change their parity and all other nodes keep their parity? Yeah? B keeps A and B. In my example, A and C change the parity. They go from 1 heavy good to 0. B keeps the parity. It goes from 0 to 2. And this was well studied in the 70s under the name parity matching. And so I mentioned that our problem is in P if S is something like, F is a half integer, and if S is more complicated, like 4 over 3, it's NP complete. This dichotomy between 2 and 3 appears elsewhere. Let's say 2 set is in P, but 3 set is NP complete. 2 disjoint path in planar graphs is in P. 3 disjoint path in planar graphs is NP complete. Matchings is easy. 3-dimensional matchings is hard. And the problem which is relevant for us is this here. So matchings with degree constraint, also called generalized matching. So for each vertex, we prescribe a set of integers. Usually this is just 0. And we ask, is there a matching, so a set of edges, M, satisfying the degree constraint, such that for every vertex V, the number of edges incident to V in M is in this set S of V. And what was shown in the 70s if all gaps have lengths less than or equal to 2, for example, S of V is the 1, 3, 5, 6, 7, then this problem is in P. If there are gaps of lengths greater or equal to 3, the problem becomes NP complete. And what we do is we use a reduction for 3-dimensional matching for the NP completeness proof for S equal to 4 over 3. and we use parity matchings in our algorithm for S an odd multiple of 1/2. Let me now come to envy-based notions. So an agent, what first comes to mind is, what did I say? Envy is nobody should get more than I do. So agent I considers an allocation fair if nobody gets more than they do. So the value of any other bundle is at most the value of the bundle which goes to I. And this is too much to ask. Again, our example from before works. 1 good and 2 agents that both like the good. You have to give it to one and then the other one will envy. So we need to go to relaxations. So relaxation means agent I considers an allocation fair if nobody gets significantly more than they do. Now, what could significantly more mean? It was first defined, relaxed to envy freeness up to 1 good. So the envy goes away after the removal of the most valuable good. So for every I and j, there is a good in xj such that the value of xj minus e is no more than the value of xi. It was shown in 2004 that such an allocation always exists. The name envy freeness up to 1 good was introduced later, but it was shown already 20 years ago that such an allocation always exists. But EF1 is unsatisfactory. Imagine the following hypothetical statement after a settlement of a bequest. Somebody says to his brother, "You will receive a house, a car, and a toothbrush. I envy you. But this is okay, as my envy disappears if I discount the house." Strange, right? So it's an unsatisfactory notion. A much more satisfactory notion is envy freeness up to any good. So envy goes away after the removal of any good. That means if you have agents I and j, for all, not for some, for all e in xj, it must be the case that if you look at xj minus e, the ice agent prefers his own bundle. It's a very demanding notion, as becomes clear if you look again at this hypothetical statement. Brother, you will receive a house, a car, and a toothbrush. I envy you. But this is okay, as my envy disappears if I discount the toothbrush. Yeah, so this is a sentence that makes a lot of sense, but EFX is a very demanding notion. Does it exist? What is known? So it is known that it always exists for 2 agents and for any number of agents with identical valuations. And I will show you the algorithm in a short while. For 3 agents and additive valuations, it always exists, as was shown by Shaduri, Garg, and myself 5 years ago. We generalized this with Hanna and Bhaskar and Jugal 2 years ago. It exists if we have 3 agents and 2 of them have general valuations. The third one needs to have a more restrictive valuation. And it's open whether it exists for 4 agents, for n agents, for 3 agents with general valuations, or whether you can have EFX and also guarantee share. And what I want to do next is I want to show you, I sketch a proof of this. Not the original proof. The original proof was quite complicated, but I take this proof and I sketch it for the additive case. What is what can be said for 4 agents? I have a computer in my office sitting who tries instances for 3 agents and general valuations, and for 4 agents and additive valuations. I have tested millions of examples. So far, an EFX allocation always exists. But yeah, what does this mean? I come back to this. So 2 general monotone valuations and 1. So this third valuation must satisfy the following property. If you split a set of goods in 2 ways, so in A and B and in C and D, then it must be the case that if you take the minimum value of A and B, it's at most the maximum value of C and D. So this is certainly true for additive valuations, because then this sum here is equal to this sum, and so the minimum is less than the maximum, because the minimum is less than 1/2 and the maximum is at least 1/2. It's true if the value of a bundle is the maximum value of a good in the bundle, because then on the right hand side you have the maximum value of any good in the entire set, and on the left hand side you have just the minimum, not the maximum, in either A or B. It's not true if they are complementary goods. So let's say A is a pair of shoes, B is a pair of shoes, C are the 2 left shoes, and D are the 2 right shoes. Then on the left hand side you have a significant value, and on the right hand side you have no value. Yeah, so if they're complementary goods, it's not true. Let me next sketch you a proof. This will be the hardest part of the talk. So the algorithm works iteratively, and we maintain the following invariant. We main a partition A, B, C, such that, so we have 3 agents, 1, 2, 3. Agent 1 is content with bundles A and B. So that means if one owns A or B, it does not strongly envy C. What does it mean? It does not strongly envy C. It means that if you remove any good from C, then it's at most the value of A. I've written here. Yeah. So A is content with bundles A and B. So if it owns A and B, it does not strongly envy C. And one of the agents 2 or 3 is content with bundle 3. So in my picture, agent 3 will be content with bundle C. This is the invariant that we maintain. And what I want to show you next is how we establish the invariant, and then how we make progress. So how do we establish the invariant? We generate a partition such that agent 1 is content with all 3 parts, and then we let agent 2 or agent 3 choose. So assume we have a division into 3 parts, A, B, and C, and for agent 1, A is the most valuable part, and then comes B, and then comes C, and C strongly envies A. That means even after the removal of a good from C, we still have A would prefer C minus E. So let's say there is a good E in A such that A minus E is still better than C for 1. And then what we do is we move E from A to C. So in this way the value of C goes up, and in fact the minimum goes up because the new A still is more valuable than the old C, so the minimum goes up. The procedure terminates, the minimum value of any bundle goes up, and at termination 1 is content with all 3 bundles, and then we let 2 or 3 choose, and we have established the invariant. So this is, we know how to establish the invariant. Now we know we're done. if I'm claiming if either agent 2 or 3 is content with A or B, we're done. Well, we first observe that each agent is content with at least one bundle, namely their favorite. If I give you the bundle that you like most, you will not envy any of the other two, and hence also not strongly envy. Now, let's see, if 2, so we are in this situation, agent 1 is content with A and B, agent 3 is content with C. If agent 2 is content with A and B, let's say agent 2 is content with B, we have a matching. We give A to 1, B to 2, C to 3. If 2 is only content with C, then agent 3, because we said either 2 or 3 is content with A and B, 2 is not, so C must be, and then we are again in the situation that we can give A to 1, B to 3, and C to 2. So we're done. So if either 2 or 3 is content with A or B, we're done. So we are in this situation up there, and 2 is also only content. So we are here in this situation. 2 and 3 are only content with bundle C, and I mean there's an obvious thing we must do. We must make bundle C less valuable, so that A and B become more attractive to 2 and 3. So what do? We look at A, and we look at the least valuable good. We look at C, and we look at the least valuable good in C for 2 and 3. So, I mean, here I wrote again that we must make C less valuable so that A and B become more attractive for 2 and 3. And we may also assume that for agent 1, the bundle B is better. Just arbitrary, to break ties. Okay, so let's say we look at bundle C, and we take the least valuable good for agent 2 and 3 in C. Then we observe, even if after the removal of E2, the agent 2 still prefers A and B. And similarly, if we remove E3, agent 3 still prefers A and B. C minus E3 is still more valuable than A and B, even after removal. Well, assume without the loss of generality that agent 3 prefers B over A. And since 3 is not content with B, there must be strong envy towards C. That means there is a bond for this E3, it must still be more valuable than B. And A is less than B for agent 3, so both of them. So C minus E3 is still the most valuable bundle for the agent 3, and C minus E2 is still the most valuable bundle for 2. So I wrote this again down here. So what we do is now we perform a thought experiment. We take this element E2 or E3 and we move it from C to A. Remember that A was the less valuable among A and B for agent 1. And there are 3 cases to consider. Namely, after we move the E2 to A, the agent 2 still prefers the C minus E2 over A plus E2. Case 2 is the symmetric case for agent 3. And case 3 is that we are not in case 1 and neither in case 1 nor in case 2. That means that C minus E3 is less valuable than A plus E2, and C minus E3 is less valuable than A plus E3. I will discuss the first case. The second case is treated analogously, and case 3 is more difficult, and I will ask you to read it. So this is what we know, and then we said we move it. So what we do is we move the good E2 to A, and we assume that the bundle C minus E3 is still the most valuable for agent 2. So agent 2 is happy with this bundle C minus E2. He will not envy any of the other two bundles. The agent 1 is happy towards the new C because the A bundle got more valuable, the B bundle stayed the same, and the C become less valuable. He did not strongly envy it before, so he doesn't strongly envy it now. But there might be an imbalance between A plus E2 and B. Namely, if you ask agent 1, it might be the case that he now strongly, that if you give him B, he might strongly envy A plus E2. So what we do is we choose a minimal subset of A plus E2, which is more valuable than A. Yeah, so we choose an A prime, which is a minimal subset of A plus E2, minimal with respect to cardinality, such that it's still more valuable than A. And then what I claim is that if we keep A prime for 1 and enlarge and give A minus A prime again to the third agent, the second agent, then we are fine. Why? Well, for the A prime it's fine, yeah, because now the B doesn't envy him anymore, because if you remove one further good from the A prime, you're below the old A, and B didn't strongly envy the old A. So this is fine. And also, if you look at this, the A minus I prime has value less than E2. So it's the total value is less than the old C, and we are in business. So we have re-established the invariant, and the minimum of the first two bundles have increased because A prime is worth more than A, and B was worth more than A by assumption. So the minimum increased. In this way we make progress, and since the minimum always increased, this cannot go on forever, and at the end we have a solution. So I mentioned I searched for a counterexample. I have checked 25 million instances, but there are many more allocations. So I've checked only a very small part. The checked fraction is 2 to the minus 20. And I will not go into this in more detail. Let me say a few words about best of both worlds guarantees. Remember that we had this randomized cut and choose for two agents. We determined one of the agents at random, and he had to cut, and the other one chooses. So this guarantees proportionality ex ante in expectation and NMS ex post. Can we do this more generally? So more generally means we want to design a lottery. The outcome of the lottery is an integral allocation, such that in expectation, every agent gets at least their proportionality share, and every outcome of the lottery satisfies a fairness criterion. And this was shown for EF1. This was shown for a half MMS for additive valuations, and we went to sub-additive valuations and have also a best of both worlds result. Let me close. Fair division is a rich source of problems. It's immediate appeal. It's very easy to define, and we all deal with it daily. It has practical relevance. In this intellectual depth, there are a large number of simply to state, but apparently hard problems. And let me close by pointing you to my YouTube channel. Thank you.